I'm going to develop the relationship between the radius of the cross-section of the rod and the stress. And so the way that I'm going to go about it is I'm going to start off with, so now that we've developed our two equations here, we can substitute in for theta. We can use the length of the rod times the strain divided by the distance from the center, and once we substitute this in for theta, we come up to equation number 3, and we have that the strain is going to equal the distance from the center, r, times the maximum strain divided by the radius of the rod, which is the r max. And we use a little trick here to develop the equation further in order to relate our stress to our distance from the center, r. And the way that we do that is by thinking in terms of our stress-strain relationship, and we have that the stress equals the shear modulus times the strain. So if we multiply each side of this equation by our shear modulus, we come out with the shear modulus times the strain equals the shear modulus times the maximum strain times our distance from the center, r, divided by the radius of the rod. And when we do that, we see now that or our shear modulus times our strain is equal to our stress. So we substitute in our stress over here, and then on the other side, you'll observe that when our strain is at a max, here, that means that our stress is going to be at a max. So shear modulus times the maximum strain is the maximum stress over our radius of the rod times our distance from the center. So from this equation, you can see that the stress is going to be proportional to the distance from the center of the rod. So our stress at the very outside, remember the stress is going to be a shearing stress. The shearing stress is going to be greatest on the outside of the rod, and that's what this is telling us. And it's going to decrease as we approach the center. And if r equals 0, our distance from the center equals 0, then there's going to be no stress. So now that we've developed a relationship between stress and our distance from the center of the rod, we can begin to develop the torque versus stress relationship. And a good way to do that is to draw the cross section of the rod and think of a force acting at a distance about the origin O here. And so wherever the elemental force is along this distance from the center is going to give you a different moment. And so I like to think of, instead of torque, I like to think of moment, because that really makes you think about the idea of force acting at a distance, and we have our r cross f to determine that. And so we have that our moment is going to equal basically the sum of the forces, the sum of the forces times its distance from the center here. And so we have our moment is going to equal the integral of the distance from the center, r, times the change in the force. And so we need to get df in terms of r in order to solve this integral. And how we're going to do that is through our stress equation, a relationship between stress and radius. So we know that the stress is going to equal to the force applied divided by the cross-sectional area. The stress is also going to equal the change in the force applied divided by the change in the area. And so doing a bit of algebraic, just basically move the dA over, and you get the change in force is going to equal the stress times the change in area. And so we're going to substitute this in for our dF, and now our equation is starting to look a little bit better. We have our moment is going to equal the integral of our distance from the center times our stress times dA. And when we look up here, we can see that our stress is going to equal basically a constant, which is the maximum stress over the maximum radius of the rod times the distance from the center, whatever that may be. And so we can substitute that in, and we have our moment equals our radius times our maximum stress over our maximum radius times our distance from the center, dA.